Hello, everyone. We're going to continue exploring quadratic functions when they're written to us in vertex form. Again, we call it vertex form because we can read the vertex from the equation. It's a handy form to work with. But in the prior work, what we're asked to do is to analyze these functions. And in the process of analysis, we would look for the x-intercepts. But sometimes we would notice parabolas where there are no x-intercepts. And it made some mathematicians rather curious because it's still possible to put a 0 in for y and to solve this equation. It's just that we're not going to get any real numbers out of it. So that's what this video is to talk about, is what happens when you try to solve an equation, but you already know there are no real numbers that are going to solve the equation. What happens? How do we deal with that? And so this is an introduction to dealing with numbers that are not real. So without any further ado, this is the image that I have of the function, and if I was doing my full analysis, I would get some information like the vertex is -1, 3, which tells me the axis of symmetry is the equation x equals -1. We could figure out the y-intercept eventually, which is going to be 0, 5, and I got that worked out here in my head. Now I need to find the x-intercepts, and what the graph says is there are none. Now what we're going to do is, instead of saying there are no x-intercepts, we're going to use the capital R real. I don't know if you remember this, but we work mostly with real numbers, capital R real, and those are numbers that we can count, or we could make into fractions, or we can make into irrational numbers by square rooting and stuff. But there is another kind of number called complex numbers, which are not technically followed under the real number category, and that's, again, what's going to happen here. So here's how it emerges. We start with the equation where we're looking for x-intercepts. Again, we're trying to find out what values of x make the function equal to 0. The answer is there are no real numbers for x that make the equation 0, but let's find out what happens anyway. We're going to subtract 3 from both sides and get 2 times the quantity x plus 1 squared on the right. Then we're going to divide both sides by 2, and this time I went decimals, but we got -1.5 equals x plus 1 squared. The question here is, if I'm going to take the square root of both sides, how do I deal with this square root of -1.5? To explore this, I look at a bunch of negative square roots, and I wanted to sort of introduce to you a couple of rules related to square roots. The first one is the square root of -1 used to be ignored as something that's not considered real, but eventually mathematicians discovered that there are some purposes, there's some uses for this kind of number. So instead of writing the square root of -1 all the time, they decided to give it a special name, a synonym, if you will. It is I, the letter I, lowercase. So when you write a lowercase I, you are getting a square root of -1. They mean the same thing. This is just easier to write and easier to work with. If I have the square root of -4, how do I deal with that? Well, it turns out when you're talking about square roots, you are allowed to separate the square roots by product. So -1 times 4 equals -4. Then -4 square rooted is the same as the square root of -1 times the square root of 4. The square root of -1 is I. The square root of 4 is 2, so we get 2 times I. As per convention, we put the letters in the back, so we have 2i is the same as the square root of -4. Even if you don't have any perfect squares, here we have -1 and the 5. I can't take the square root of 5, but I can call the square root of -1 I instead, so I just write I square root of 5. We don't put the I in the back. Remember, we put square roots last, so we know where the square root ends. So just a couple more examples to illustrate. -27 is really the product of -1, 9, and 3. The -1 becomes I, the 9 becomes 3, and the square root of 3, I don't know, so I leave it as square root of 3. Here again, you can see a couple more examples of the same truth. So what we do when we have to take the square root of a number like this is we break it into positive negatives, or perfect squares and non-perfect squares, and then we square root what we can, and we leave alone what we can't. It's that simple. So if we were going to go back to the problem we were working on, we have everything right up to here, and we were supposed to take the square root of both sides. So now all we have to do to finish is just take the square root of -1 and call it I, take the square root of 1 1/2 and call it the square root of 1 1/2, or 3/2. I like fractions better. On the right-hand side, nothing changes. We take the square root of a squared variable. We have to consider it could have been negative or positive. So once we have the absolute value to get rid of it, we consider the positive scenario or the negative scenario. Multiply this one by -1, so we can write as a singular equation showing 2 different solutions, x plus 1 equals plus or minus I square root of 3/2. And those are the solutions. They are the non-real x-intercepts for this particular parabola. Now there's a geometric interpretation here, but I'm going to save that for a later video or a later conversation. But for now, just accept this is the way, this is what I'm looking for if I ask you to find x-intercepts that are not real. And to drive the point home, I've got another example here. I'm just going to let it play and talk real quickly as it unfolds. So we start off with an expression of what is the graph going to look like. So we have an idea. We have the vertex at negative 2, 1, the axis of symmetry at negative 2. The y-intercept is 0, 13. Now for the x-intercepts. Again, my graph seems to indicate there will be no real x-intercepts. Nonetheless, I subtract 1 from both sides, divide both sides by 3, square root of both sides. Remember, they take the absolute value on the right. On the left, we have, instead of square root of negative 1/3, we have I square root of 1/3. And we do the positive situation, the negative situation, regroup, and solve. What makes this fun is I can actually take one of these two solutions. One's negative 2 plus I square root of 1/3. One's negative 2 minus I square root of 1/3. I can take one of those two solutions and put them back into the equation, and it should give me 0. Now here again, you can see that there's no real number x that makes this function equal 0. Yet there is a non-real number x that will in fact make the function equal 0, and I'll prove it. We have 3 times the quantity negative 2 plus negative square root of 3. So I took the I and put it back under the square root. And then we have plus 2. So this was the x value that I had, and this was the original function's 2. Square it, add 1. Turns out inside negative 2 plus 2, those 0 out, and so now we have 3 times the square root of negative 1/3 squared, plus 1. I learned in high school that the square and the square root are inverses. They undo one another, so the square root and the square negate, and we're left with 3 times negative 1/3 plus 1, which is negative 1 plus 1, which is 0. So here you see actually a non-real number can be put into a function equation and get a very real result. So that's just something that you'll get used to as time goes on. I take all the information as before, and I make a nice high-quality graph out of it as well, and even make sure that the graph is high quality. I go over 1, up 3, because my a value is 3, and I make sure that that's also a point on my graph. But, yeah, thanks for watching. Oh, yeah, by the way, here, this is going to be on PDF form on our Haiku page, and all of these functions are going to have imaginary x-intercepts. So if you want to have practice getting solutions, even if the solutions are not real numbers, here's where you can find it. If you can't find the PDF, just pause the screen and screen capture it, and you have your homework ready to go. Thanks for watching.